The fading light of the universe. An extended introduction to the end of time. To fully understand the ultimate end of the universe, we must first consider its beginning. The Big Bang Theory is widely accepted as the event that marked the birth of both space and time. About 13.8 billion years ago, the universe we know arose from an unimaginably dense and hot singularity. But what exactly is a singularity? A singularity is a point where the known laws of physics break down. In the case of the Big Bang, this singularity was a point of infinite density and temperature in which all the matter and energy of the universe was concentrated. The idea of time before the Big Bang becomes meaningless because time itself began as the universe expanded. There is no before in any meaningful sense. It's not that time existed and then the Big Bang happened. Time itself began at that moment. As the universe expanded, it cooled, and the fundamental forces we observe today, gravity, electromagnetism, and the nuclear forces, emerged from the original energy of the early universe. In the first fraction of a second after the Big Bang, the universe experienced a period of cosmic inflation in which it expanded exponentially in an incredibly short period of time. This phase of inflation smoothed the universe and created the conditions for the formation of galaxies, stars, and planets. In those early moments, a sea of particles, mostly quarks, leptons, and gluons, filled the universe. As the universe continued to cool, quarks combined to form protons and neutrons, which then merged to form atomic nuclei. The universe entered a phase known as recombination about 380,000 years after the Big Bang, in which electrons combined with nuclei to form neutral atoms. This allowed photons, particles of light, to move freely, resulting in the cosmic background radiation, CMB, the faint afterglow of the Big Bang that we can still observe today. Fast forward to the 20th century, when a monumental discovery changed our understanding of the universe, the expansion of the universe. In the early 1920s, astronomer Edwin Hubble observed that distant galaxies were moving away from us. Not only that, the further away a galaxy was, the faster it seemed to be moving away. This relationship, now known as Hubble's law, provided the first direct evidence that the universe is expanding. Hubble's observations were based on the redshift of light from distant galaxies. Light behaves like a wave, and just as the sound of a siren changes as it moves toward or away from us, the wavelength of light from distant galaxies also changes depending on their movement. As a galaxy moves toward us, its light becomes blue-shifted, the wavelength shortens, and as it moves away, its light becomes red-shifted, the wavelength lengthens. The fact that almost all galaxies were redshifting suggested that the universe was expanding, stretching the fabric of space itself. Hubble's discovery led to the realization that the universe must have been smaller in the past, which eventually converged into a single point, the Big Bang. This confirmed the idea that the universe has a finite age, and therefore a possible final destination. But what is driving this expansion, and what does it mean for the future of the cosmos? To answer this question, we need to understand the mysterious force known as dark energy, which we will examine in detail later. Is the expansion of the universe finite or infinite? As the universe continues to expand, scientists are asking themselves profound questions. One of the most important is whether the universe is finite or infinite. If the universe were infinite, that would mean that it was always unbound and would forever remain infinitely expanded in all directions. If it were finite, that would suggest that the universe has a limit or edge, even if it is beyond our ability to observe. To answer this question, physicists study the curvature of space. Einstein's general theory of relativity tells us that space can be curved, similar to the surface of a sphere. The curvature of space is determined by the density of the universe. If the density of the universe is higher than a critical value, space would curve inward, much like a sphere, and the universe would eventually stop expanding and collapse in on itself. The Great Collapse. If the density reached exactly the critical value, the universe would be flat and expand forever. If the density is lower than the critical value, space would curve outward, similar to a saddle, and the universe would expand indefinitely, potentially leading to the Great Freeze or Great Ripping. Current measurements suggest that the universe is remarkably close to a flat curvature, but whether it is exactly flat, open, or closed remains an open question. If the universe is infinite, this would mean that expansion is happening everywhere at once, creating new space between galaxies, but it remains impossible for us to fully observe. One of the challenges in understanding the expansion of the universe lies in measuring the vast cosmic distances. Astronomers use a method known as the cosmic distance ladder to calculate distances to distant objects. This ladder consists of a series of techniques, each building on the previous one, to expand our ability to measure distances from nearby stars to the most distant galaxies. The first step of the ladder involves parallax, where we observe a star from different positions in Earth's orbit and use trigonometry to calculate its distance. For more distant stars, we rely on standard candles, such as Cepheid variable stars and type Ia supernovae, whose intrinsic brightness is known. By comparing their intrinsic brightness with their apparent brightness as seen from Earth, we can calculate their distance. For even more distant galaxies, astronomers turn to redshift measurements and rely on Hubble's law to estimate how far these galaxies have receded. These combined techniques allow us to map the structure of the universe and understand its expansion. As the universe expands, the question remains, what will happen to time itself? If the universe expands indefinitely, will time continue forever? Or is there a point at which time will cease to have meaning? This leads us to the concept of cosmic time, a universal time parameter that applies to the entire universe. As the universe expands and cools, time advances, marked by the evolution of stars, galaxies, and black holes. But in a scenario like the Great Freeze, in which the universe cools to the point where thermodynamic processes no longer occur, time itself could lose its relevance. Time, as we perceive it, is closely linked to change. If nothing changes in the distant future, the flow of time could become an empty concept. Time could continue to exist, but without events to mark its course, it would become irrelevant. On our journey, we will continue to explore how the one-dimensional direction of time is determined by a principle called entropy, and how the ultimate fate of the universe is tied to this profound concept. The Arrow of Time, a deeper exploration of the irreversibility of time. As previously mentioned, entropy is the key to understanding why time only seems to flow in one direction, forward. But what exactly is entropy, and why does it play such a crucial role in the future of the universe? The concept of entropy arises from the second law of thermodynamics, one of the most fundamental principles of physics. This law states that the total entropy or disorder of a closed system can never decrease over time. In simpler terms, systems evolve from states of order to states of disorder, and this irreversible increase in entropy results in the progression of time. Let's look at an example. Imagine you have a glass of hot water and an ice cube. When you drop the ice cube into the water, the ice melts and the water cools until both reach the same temperature. This is an irreversible process. You will not see the ice cube spontaneously reform and the water heat up. The system has moved from a low entropy state, separated hot water and ice, to a higher entropy state, evenly distributed temperature. This increase in disorder is what we perceive as the flow of time. In the context of the universe, entropy increases on a cosmic scale. In the early universe, matter was highly ordered and concentrated in a dense, hot state. But as the universe expanded and cooled, galaxies formed, stars burned, and matter spread out, increasing the overall entropy of the universe. Over billions of years, this process will continue. Stars will eventually fade out, and black holes will slowly evaporate, contributing to the universe's inexorable march toward maximum entropy. The idea of increasing entropy leads directly to one of the most widely discussed scenarios for the end of the universe: heat death, also known as the Great Freeze. As the universe expands and entropy increases, it will eventually reach a state in which all available energy is evenly distributed. In this state, no more work can be done, no more stars will burn, no more galaxies will collide, and no more life will be able to exist. The universe becomes a cold, dark place, with only faint remnants of energy left. The heat death scenario relies on the fact that energy flows from hot to cold objects, a process that increases entropy. Once the universe reaches thermodynamic equilibrium, where heat flow is no longer possible, there will be no more usable energy to power stars, galaxies, or life. In this final state, time could theoretically continue to exist, but since there are no events to mark its passage, the concept of time as we understand it would lose its meaning. In addition to stars and galaxies, black holes also play a role in the history of entropy. As we mentioned in the previous chapter, black holes are regions of space-time where gravity is so strong that nothing can escape, not even light. But black holes aren't just cosmic vacuum cleaners, they also have entropy. In 1974, Stephen Hawking made a groundbreaking discovery when he showed that black holes emit radiation, now known as Hawking radiation. This radiation causes black holes to lose mass and energy over time, meaning they eventually evaporate. But this process is incredibly slow. For most black holes, it would take far longer than the current age of the universe to completely evaporate. Hawking's discovery revealed a profound connection between black holes and entropy. Black holes are the most ordered objects in the universe and contain enormous amounts of information about the matter they absorb. But as they emit Hawking radiation, they gradually increase the entropy of the universe. In the distant future, when all the stars have gone out, black holes will be the last sources of entropy, slowly leaking energy back into the cosmos as they evaporate. Let's imagine a thought experiment. What if time could be reversed? If entropy is the key to the direction of time, could reversing entropy also reverse time? Imagine a universe where the second law of thermodynamics is reversed, where systems naturally move from states of high entropy, disorder, to states of low entropy, order. In this universe, broken objects would reassemble themselves, stars would burn out, and galaxies would contract into dense, ordered states. From our perspective, time would run backwards in this universe. But is this scenario physically possible? According to our current understanding, it is not. The second law of thermodynamics is one of the most fundamental principles in the universe, and there are no known processes that can reverse entropy on a large scale. Theoretically, individual particles can move in ways that reduce entropy, but for large systems, the general trend is always toward greater disorder. This leads us to another fascinating paradox. If time is linked to entropy, then why was the early universe in such a low state of entropy? The Big Bang created an incredibly ordered universe, but as it expanded, entropy increased. Understanding why the universe began in such an orderly state is one of the greatest unsolved mysteries in cosmology. Could there be universes in which the laws of entropy, and consequently the flow of time, are different? If we consider the multiverse hypothesis, it is possible that there are other universes where time works differently. In some universes, entropy could decrease over time, causing time to flow backwards. In others, time might not exist at all. In our universe, the arrow of time points in one direction because entropy increases. But in a multiverse, time could work in radically different ways. This raises the intriguing possibility that in some regions of the multiverse, time could be reversible or even circular, spinning endlessly as the universe goes through cycles of creation and destruction. As we continue to move forward, the concepts of dark energy, entropy, and time intertwine, shaping the ultimate fate of the universe. Whether time continues indefinitely or loses meaning in the distant future, the flow of entropy offers us a window into the deep structure of reality. Dark energy, the driving force behind the expansion of the universe. As we continue our journey through the cosmos, we encounter one of the greatest mysteries in modern astrophysics: dark energy. This elusive and mysterious force is believed to be responsible for the accelerated expansion of the universe, a discovery that has fundamentally changed our understanding of cosmology and the ultimate fate of the cosmos. But what exactly is dark energy, and how does it influence the possible end of the universe? In 1998, two independent teams of astronomers made a stunning discovery while studying distant supernovae. They found that the universe wasn't just expanding, it was accelerating. This contradicted all previous expectations. According to previous models, the expansion of the universe, driven by the energy of the Big Bang, should have slowed down over time due to the gravitational pull of matter. But the supernova data suggested the opposite. The universe was speeding up, and something mysterious had to be responsible. This is where dark energy comes into play. This term was coined to describe the unknown force that is pushing galaxies apart at increasing speeds. Today, it is estimated that dark energy accounts for about 70% of the total energy content of the universe. Despite their overwhelming presence, we know very little about them. Unlike dark matter, which interacts with normal matter through gravity, dark energy does not appear to interact with matter at all, other than accelerating the expansion of space itself. To understand how dark energy affects the fate of the universe, let's consider the so-called cosmological constant. Originally introduced by Albert Einstein in 1971, the cosmological constant was a term in his equations of general relativity that represented a repulsive force that counteracts gravity. At the time, Einstein believed the universe was static and unchanging, and he used the cosmological constant to balance the universe and prevent it from collapsing under its own gravity. However, after Edwin Hubble's discovery of the expanding universe in the 1920s, Einstein infamously called the cosmological constant his biggest mistake and abandoned the idea. But with the discovery of the accelerating universe in the 1990s, the cosmological constant made a comeback. It turns out that a form of energy that permeates all of space and exerts a constant repulsive force could explain the observed acceleration. We now call this form of energy dark energy, and the cosmological constant is a possible explanation for its nature. But the story of dark energy does not end with the cosmological constant. Some scientists have proposed alternative models to explain the accelerated expansion. One of these models involves a dynamic form of dark energy known as quintessence. Unlike the cosmological constant, which remains constant over time, the strength of the quintessence is believed to change as the universe evolves. If the bottom line turns out to be correct, it could have profound implications for the future of the universe. Now let's take a step back and consider the bigger question. How does dark energy affect the ultimate fate of the universe? The answer depends on several factors, including the strength of dark energy and how it evolves over time. There are several possible scenarios, each offering its own idea of the end of the universe. One of the most widely accepted scenarios is the Great Freeze, which we have already briefly mentioned. In this model, dark energy drives the expansion of the universe indefinitely. As time passes, galaxies become further and further apart, stars burn out, and the universe becomes cold and dark. As the cosmos's energy sources are depleted, new stars will no longer be able to form, and all matter will eventually expand to such an extent that it will become impossible for life or even complex structures to exist. In the distant future, billions and billions of years from now, the black holes themselves will evaporate due to Hawking radiation, leaving behind a universe consisting only of faintly glowing particles that will slowly drift apart into an ever-growing void. This is the ultimate heat death of the universe, a state of maximum entropy in which all energy is evenly distributed and no more work can be done. Another, more dramatic scenario is the Great Rending. In this model, dark energy grows stronger over time, eventually tearing apart the fabric of space-time itself. While the cosmological constant implies a uniform rate of expansion, the Great Rip scenario involves an acceleration that increases indefinitely. The main difference between the Great Freeze and the Great Rend lies in the behavior of dark energy. In the Great Rend, dark energy becomes increasingly dominant and overwhelms all other forces in the universe. Imagine a future in which galaxies are torn apart, then solar systems, planets, and finally, atoms themselves. As dark energy accelerates the expansion of space, everything is stretched to the breaking point. The forces that hold matter together, such as gravity and electromagnetism, would be overwhelmed, and even fundamental particles could be torn apart. In the final moments of the Great Ripping, the universe would become a chaotic, decayed space in which no coherent structures would exist. Current observations suggest that the Great Ripping is less likely than the Great Freeze, but it remains a theoretical possibility. If dark energy behaves like quintessence and increases in strength over time, the Great Rending could become a reality. In contrast to the endless expansion predicted in the Great Freeze and the Great Rupture, there is another possible fate: the Great Collapse. This scenario imagines that the universe eventually reverses its expansion and collapses back in on itself. In the Great Collapse, dark energy is either weak or absent, and gravity, the attractive force that holds matter together, ultimately wins the cosmic battle. Over time, the expansion of the universe would slow and stop, and then the universe would begin to contract. Galaxies would move closer together, stars would collide, and temperatures would rise as matter was compressed. Eventually, all matter and energy would collapse into a singularity, a point of infinite density, similar to the state of the universe at the time of the Big Bang. The Great Collapse presents a cyclical view of the life cycle of the universe. After the collapse, it could be possible for a new Big Bang to occur, restarting the universe in a perpetual cycle of expansion and contraction. This idea ties in with theories of a cyclic universe, in which the universe goes through repeated cycles of creation, destruction, and rebirth. The Great Rebound is a variant of the cyclic universe theory in which the universe alternates between phases of expansion and contraction. In this model, the universe reaches a maximum size, contracts to a minimum point, and then jumps back into expansion. Each cycle of expansion and contraction is said to produce a new universe with different physical properties, constants, and possibly different laws of nature. Unlike the Great Collapse, the Great Rebound does not end in a singularity. Instead, the universe avoids the infinite density of a singularity and jumps back into a new phase of expansion. Some theorists suggest that the Great Rebound could be driven by quantum effects that prevent the complete collapse of space-time. While the Great Rebound is a speculative idea, it offers a hopeful view of the fate of the universe, one in which the end of time is never truly reached, but instead gives way to new beginnings. As we ponder the role of dark energy, it becomes clear that this mysterious force is key to understanding the future of the cosmos. Whether the universe ends in a cold, desolate great freeze, a catastrophic great rift, or a fiery great collapse, dark energy will play a crucial role in shaping the final chapter of cosmic history. But our understanding of dark energy is still in its infancy. Future observations and experiments could reveal more about their nature and behavior, allowing us to refine our predictions about the fate of the universe. For now, we are left with more questions than answers. Will dark energy remain constant, as described by the cosmological constant? Or will it evolve and lead to new and unexpected consequences? In the next chapter, we will delve into one of the most fascinating aspects of the future of the universe: the fate of black holes. Not only are these cosmic giants some of the most enigmatic objects in the universe, but they could also hold the key to understanding the long-term evolution of space-time itself. Black holes, the ultimate rulers of the universe. As we continue our exploration of the potential end of the universe, we turn to one of the most fascinating and mysterious objects in the cosmos: black holes. These cosmic giants are not only the ultimate consumers of matter, but also play a crucial role in the long-term fate of the universe. In the distant future, when the stars have gone out and the galaxies have drifted apart, black holes could be the last remnants of the universe as we know it. What are black holes? To understand the role that black holes will play in the ultimate fate of the universe, we must first understand what they are. A black hole is a region of space-time where gravity is so intense that nothing, not even light, can escape. The boundary of this region is called the event horizon, beyond which all information is lost to the rest of the universe. At the center of a black hole is a singularity, a point of infinite density where the laws of physics as we understand them collapse. Black holes arise from the collapse of massive stars at the end of their life cycle. Once a star has used up its nuclear fuel, it can no longer sustain itself against gravity. For stars with a mass greater than about 3 times the mass of the Sun, this collapse results in the formation of a black hole. Black holes come in a variety of sizes, from stellar black holes formed by the death of massive stars, to supermassive black holes found at the centers of galaxies that can have masses equal to billions of suns. The origin of supermassive black holes remains a mystery, but they are thought to have formed in the early universe, possibly through the merger of smaller black holes or through the direct collapse of large gas clouds. As stars burn out and galaxies drift apart due to the expansion of the universe, black holes become increasingly dominant. Over the next trillion years, As the stars exhaust their nuclear fuel and no longer shine, the cosmos will become darker. Some stars could collapse into white dwarfs or neutron stars, while others could end up as black holes. In the distant future, black holes will be among the last remaining objects in the universe. But black holes, despite their tremendous gravitational pull, are not eternal. In 1974, physicist Stephen Hawking made a groundbreaking discovery. Black holes emit radiation. This phenomenon, now known as Hawking radiation, arises from quantum mechanical effects near the event horizon. According to quantum mechanics, pairs of virtual particles constantly emerge and disappear again. Near a black hole, one of these particles can fall into the black hole while the other escapes, drawing energy from the black hole and causing it to lose mass over time. This process is incredibly slow. For a typical stellar mass black hole, it would take far longer than the current age of the universe to completely evaporate. But in the distant future, when most stars are extinct and the universe is mostly empty, the gradual evaporation of black holes could become a significant process. Over unimaginably long periods of time, far longer than the current age of the universe, even the largest black holes will eventually evaporate due to Hawking radiation. As they lose mass, they will shrink in size, and their evaporation rate will accelerate. The final moments of a black hole's life would be accompanied by a burst of radiation as it releases its last remaining energy. For supermassive black holes containing millions or billions of solar masses, this process will take an unimaginably long time, tens to hundreds of trillions of years, depending on the size of the black hole. But eventually, even these cosmic giants will disappear. After the last black hole, the universe will remain in a state of almost absolute darkness. Only a few subatomic particles and weak radiation will remain, spread over vast distances. This marks the era of black holes, one of the final phases of the universe's evolution, in which all matter and energy has been absorbed or radiated and no new structures can form. Do black holes erase information? One of the biggest unsolved mysteries associated with black holes is the information paradox. According to quantum mechanics, information about the state of a physical system must always be preserved. But when an object falls into a black hole, all information about its physical state appears to be lost forever once it crosses the event horizon. When the black hole eventually evaporates due to Hawking radiation, where does this information go? This problem has puzzled physicists for decades. Stephen Hawking initially believed that information was actually lost in black holes, which would violate the principles of quantum mechanics. However, newer theories suggest that information could potentially be encoded in the event horizon or preserved in the radiation emitted by the black hole. This remains an active area of research with no definitive answer. If information is lost in black holes, it would challenge our understanding of the fundamental laws of physics. Some theories, such as the holographic principle, propose that the information about anything that falls into a black hole is stored on the two-dimensional surface of the event horizon, similar to a hologram. This would mean that the three-dimensional world we experience is a projection of this two-dimensional information. Solving the information paradox could have profound implications for our understanding of the ultimate fate of the universe. If black holes erase information, this could mean that the final state of the universe corresponds to complete simplicity, in which all complexity and structure are erased. However, if information is preserved, it could suggest a deeper, underlying order in the cosmos, even in its final moments. Black holes don't just devour matter, they also play a crucial role in shaping galaxies and thus the universe. Supermassive black holes at the centers of galaxies are thought to regulate the formation of stars and the distribution of gas throughout the galaxies. Through the process of accretion, in which matter spirals into a black hole, these cosmic giants can release enormous amounts of energy in the form of jets and radiation that can heat the surrounding gas and prevent it from collapsing to form new stars. This feedback process is crucial for the evolution of galaxies. Without supermassive black holes, galaxies could form stars indefinitely, ultimately using up all their gas in the process. By regulating star formation, black holes ensure that galaxies have long lifetimes, but they also limit the total number of stars that can form. In the distant future, when black holes dominate the universe, their ability to form cosmic structures will fade. Once the gas in the galaxies is used up, new stars will no longer form, and black holes will no longer influence their surroundings in the same way. In this sense, black holes will outlast the structures they once helped create. Could we use black holes as portals? Beyond their role as cosmic consumers, black holes have captured the imagination of scientists and science fiction enthusiasts alike, who imagine that they could serve as gateways to other regions of space-time. Theoretical physicists have speculated that black holes could be connected to wormholes or serve as entrances to other universes. A wormhole is a hypothetical tunnel through space-time that could connect two distant regions of the universe or even link our universe to a completely different one. Wormholes are predicted by Einstein's general theory of relativity, but no evidence of their existence has yet been found. Some theories suggest that black holes may contain wormholes, although any attempt to enter a black hole would likely end in being crushed by the immense gravitational force long before such a tunnel is reached. While the idea of using black holes as cosmic shortcuts is tempting, it remains firmly in the realm of speculation. Nevertheless, the study of black holes has provided deep insights into the nature of space, time, and gravity, and expanded the boundaries of our understanding of the universe. As the universe continues to expand and cool, black holes are gradually becoming the last remaining significant structures. The black hole era will last unimaginably long, far beyond the lifespan of stars, galaxies, and any life that might exist in the universe. Ultimately, however, the black holes will also disappear. The universe will remain in a state of complete entropy, a dark, cold void with no significant structures, no energy to power new processes, and no way for life to survive. This will be the end of time as we know it. But is this really the end? Some cosmologists speculate that even in this final state, quantum fluctuations could give rise to new universes, potentially triggering a new Big Bang and beginning the cycle of cosmic evolution again. Whether this will happen remains one of the great mysteries of the cosmos. In the next chapter, we will explore the final frontier of the fate of the universe, the multiverse hypothesis. Could our universe be just one of many? And if so, what does that mean for the end of time? The multiverse hypothesis. Are we just one of many universes? As we approach the possible end of the universe, it is important to consider one of the most fascinating and speculative ideas in modern cosmology, the multiverse hypothesis. This theory suggests that our universe may not be the only one. Instead, it could be just a bubble in a vast, possibly infinite sea of universes, each with its own physical laws, constants, and perhaps even dimensions. But what does this mean for the end of time? Could other universes exist beyond the ultimate fate of our own? What is the multiverse? The concept of the multiverse comes from different areas of physics, each of which provides its own version of what multiple universes might look like. Let's explore some of the main multiverse models. The most widely accepted version of the multiverse comes from the theory of cosmic inflation, first proposed in the early 1980s by physicist Alan Guth. Inflation states that in the moments after the Big Bang, the universe went through a phase of exponential expansion that grew faster than light. This rapid inflation smoothed the universe and explains why it appears so uniform on large scales. But inflation doesn't necessarily end everywhere at the same time. In some regions, inflation could last indefinitely, creating new pocket universes. Each of these pocket universes would stop expanding at different times, creating a vast multiverse in which our universe is just one of many. These universes could have different physical constants, like the speed of light or the strength of gravity, which could lead to completely different types of physics and matter. Another version of the multiverse comes from the strange world of quantum mechanics. In quantum mechanics, particles exist in a superposition of all possible states until they are observed, at which point the superposition collapses into a single state. But what if instead of collapse, each possible outcome actually occurs in its own separate universe? This idea is known as the many worlds interpretation of quantum mechanics, proposed by physicist Hugh Everett in 1957. According to this interpretation, every time a quantum event occurs, the universe splits into multiple versions, each representing a different outcome. For example, in one universe, a particle decays, while in another, it does not decay. Over time, this branching process creates an infinite number of parallel universes, each with its own unique history and future. In one of these universes, you may be reading this script somewhere else, or perhaps not reading it at all. In string theory, a leading candidate for a theory of everything, our universe could be one of many branes, short for membranes, floating in higher dimensional space. In this brane world scenario, our universe is like a three-dimensional surface, a brane, that exists in a higher dimensional space. Other branes, representing other universes, could exist parallel to ours, perhaps separated only by a tiny distance in an invisible additional dimension. These parallel universes or brain worlds could have their own sets of physical laws and constants. Occasionally, these brains could collide, potentially triggering a new Big Bang. Some theorists even suggest that the Big Bang itself was the result of such a collision between brains in the distant past. Each of these multiverse models offers a radically different picture of reality and challenges our understanding of the universe and our role in it. But how do these ideas relate to the fate of our universe? How could the multiverse influence the end of our universe? If our universe is part of a larger multiverse, this raises profound questions about what the end of time might look like. In a single universe model, the death of the universe, whether by the Great Freeze, the Great Rift, or the Great Collapse, seems to be a final, inescapable fate. But in a multiverse, the end of our universe could be just a small event in a much larger cosmic landscape. One possibility is that other universes within the multiverse may continue to exist indefinitely when our universe reaches its end. These other universes could be completely different from our own, with different physical laws and perhaps even different concepts of time and space. The thermal death of our universe could hardly matter in the grand scheme of the multiverse, since countless other universes could continue to thrive. There's also the intriguing idea that new universes could arise from the death of old ones. In the cyclic universe model, for example, the universe goes through repeated cycles of expansion and contraction, with each great collapse followed by a new Big Bang. If the multiverse works in a similar way, the death of our universe could trigger the birth of a new one, either in the same cosmic region or in a completely different part of the multiverse. In some multiverse theories, universes are constantly being created through inflation, even as old ones die. This leads to the concept of eternal inflation, where the multiverse is an ever-expanding, ever-evolving sea of universes. Our universe may just be a bubble created during a brief pause in inflation, while new bubbles continue to form and grow elsewhere. In this scenario, the death of our universe would be just a fleeting moment in an infinite, ongoing process of universe creation. The multiverse also complicates our understanding of time itself. In our universe, time appears to flow in a single direction, from the past to the future, driven by the increase in entropy, as we discussed in Chapter 2. But in a multiverse, the concept of time could be different in each universe. In some universes, time could flow backwards. In others, there might be no time at all, or time might function in ways we cannot even imagine. Some physicists speculate that time is a local phenomenon that only exists within individual universes. Outside our universe, in the larger multiverse, there could be no concept of time as we understand it. The birth and death of universes could occur simultaneously from the perspective of the multiverse, with no clear sequence of events. This would mean that the end of time in our universe is not actually the end. It is just the end of time as we experience it within the specific boundaries of our universe. Can we prove the existence of the multiverse? One of the biggest challenges facing the multiverse hypothesis is the question of evidence. Since other universes would lie beyond the observable horizon of our own, it is unclear whether we could ever prove their existence. Some scientists argue that the multiverse is not testable and therefore does not constitute a valid scientific theory. Others believe that indirect evidence may eventually be found, perhaps through subtle imprints on the cosmic background radiation, the afterglow of the Big Bang, or through gravitational waves. In recent years, there have been some promising hints that the multiverse could leave detectable traces. Some researchers have suggested that the collision of two universes in the distant past may have left a damage to the cosmic background radiation, a faint imprint that could be measured with future telescopes. Likewise, gravitational waves, ripples in space-time caused by massive cosmic events, could carry information about other universes. While these ideas remain speculative, the search for evidence of the multiverse is pushing the frontiers of cosmology and theoretical physics. If we could confirm the existence of the multiverse, it would revolutionize our understanding of reality and place our universe in a much larger context. What would life be like in another universe? Let's imagine for a moment that you could travel to another universe in the multiverse. What would you find? Would the physical laws be similar to those of our own universe, or would they be completely alien? Could life as we know it exist in such a universe, or would the conditions be so different that life would be impossible? One of the most fascinating aspects of the multiverse hypothesis is that it allows for an infinite variety of possibilities. In some universes, the constants of nature could be so finely tuned that life forms very similar to ourselves could emerge. In others, the laws of physics may prevent the formation of atoms or stars, leading to universes containing nothing but cold, empty expanses. If the many worlds interpretation of quantum mechanics is correct, there could even be universes in which alternate versions of you exist, living different lives due to different quantum mechanical outcomes. Maybe in one universe you made a different decision at a crucial moment, resulting in a completely different future. The multiverse also opens up the possibility of universes with additional dimensions or completely different geometries. In some string theory models, universes could have more than the three spatial dimensions we are familiar with. These higher dimensional universes may be impossible for us to perceive or interact with, but they may be just beyond our reach. Ultimately, the multiverse hypothesis suggests that the end of time may not be the final word in our universe. If other universes continue to exist, or new ones continually emerge, the death of our universe could be just a small part of a much larger and more complex cosmic story. Time as we experience it may be a fleeting phenomenon in the vastness of the multiverse. As we ponder the possibility of the multiverse, we are left with more questions than answers. Could there be other versions of ourselves in different universes? Will the multiverse continue to spawn an infinite number of new universes? And perhaps most intriguingly, if the multiverse exists, what does that mean for the concept of reality itself? In the next chapter, we will explore one final speculative idea: the possibility that our universe is not a physical entity, but a simulation. Could our entire cosmic history, from the Big Bang to the end of time, be nothing more than a complex program running on an unknown, advanced system? The simulation theory. Is the universe just a complex program? As we approach the final stages of our journey to the possible end of the universe, we turn to one of the most fascinating and controversial ideas in modern philosophy: simulation theory. This theory suggests that the universe we experience, from the smallest particles to the largest galaxies, may not be a physical reality, but rather a sophisticated simulation running on an unimaginably powerful computer. Although the idea of living in a simulation sounds like science fiction, it has attracted serious attention from philosophers, scientists, and even technology entrepreneurs like Elon Musk. But how is this hypothesis related to the end of time? And if we live in a simulation, what happens when the simulation ends? What is simulation theory? Simulation theory was most famously formulated by philosopher Nick Bostrom in the year 2003. In his paper, Bostrom hypothesized that one of the following three statements must be true: the probability of a species like humanity reaching a post-human stage of development, in which it would be able to conduct large-scale simulations of conscious beings, is almost zero. When a species reaches a post-human stage, the probability that it will choose to run simulations of its ancestors is also almost zero. If post-human civilizations are capable of running simulations and choose to do so, then the number of simulated realities would far exceed that of the real ones, meaning that we are much more likely to live in a simulation than the base reality. Bostrom's argument is based on the idea that future civilizations with advanced computing technologies might be able to simulate entire universes, including conscious beings like us. If such simulations were common, the chances of us living in the base reality, the original unsimulated universe, would be astronomically small. Although simulation theory is largely philosophical, some scientists have pointed to various oddities in the universe that could indicate that we are living in a simulation. For example, the universe appears to be governed at its most fundamental level by elegant and precise mathematical laws. From the equations of quantum mechanics to the structure of space-time and general relativity, the fabric of reality appears to be deeply connected to mathematics. Some proponents of simulation theory argue that this mathematical structure is evidence that the universe is a computational simulation, where the code of the simulation appears as the physical laws that we observe. Some physicists have suggested that space-time itself may be quantized. That is, that there is a smallest possible unit of space and time, similar to the pixels in a digital image. If space-time is indeed pixelated in this way, it could indicate that our universe is based on a discrete grid, similar to the way computer simulations depict virtual worlds. The smallest possible unit of space is known as the Planck length, about 10 to the minus 35 meters, and if space-time is quantized at this scale, this could indicate that the universe is a computational construct. One of the strangest features of quantum mechanics is the idea that particles exist in a superposition of states until they are observed. This begs the question, why does the act of observation cause a quantum system to collapse into a single state? Some proponents of simulation theory suggest that this behavior is similar to how video games or simulations render objects only when observed by the player in order to conserve computing resources. In this view, quantum indeterminacy could be a sign that the universe is optimizing its resources by not fully rendering unguarded realities. The Fermi paradox refers to the apparent contradiction between the high probability of the existence of extraterrestrial civilizations in the galaxy and the lack of evidence of or contact with such civilizations. One possible explanation for the Fermi paradox is that we live in a simulation and the programmers of the simulation have decided to limit or exclude the presence of extraterrestrial life. In this sense, the absence of aliens could be an intentional feature of the simulated universe designed to create a more convincing or understandable narrative for us, the inhabitants. If we accept the possibility that we are living in a simulation, it opens up new possibilities for how the universe and time itself could end. In a simulated reality, the ultimate fate of the universe is not necessarily tied to physical processes such as the expansion of space or the evaporation of black holes. Instead, it could be dictated by the whims of the simulation's creators. Here are some speculative scenarios for the end of time in a simulated universe. The most obvious possibility is that the beings running the simulation might one day decide to shut it down. This could happen for a variety of reasons. Perhaps the simulation has served its purpose, or the creators have lost interest, or their own civilization is facing extinction. If the simulation is turned off, our universe would immediately cease to exist. From our perspective, time would simply stand still, with no warning or sign that something was wrong. Like any complex computer program, the simulation that runs our universe could experience technical glitches or failures. A catastrophic error in the simulation's code could cause the universe to behave unpredictably, with the laws of physics breaking down or time itself becoming irregular. If the simulation crashes completely, the universe could experience a sudden and violent end, with all matter and energy disappearing in an instant. In some versions of simulation theory, the universe could undergo periodic restarts or resets. After a long period of time, the simulation could be reset to its initial conditions, starting the cosmic cycle again. This would be similar to restarting a video game after completing it. If the simulation restarts, we could never be aware of it. The new simulation would begin with no memory of the previous one. Another possibility is that the beings running the simulation could decide to update it, add new features, or refine its laws. In this scenario, the end of our current universe may not be the true end, but rather the transition to a new version of the simulation. The new universe could have different physical laws, or we could experience changes in the fabric of reality itself. 」 . From our perspective, these changes could manifest as sudden shifts in the behavior of matter, energy, or time. Simulation theory raises profound questions about the nature of reality, free will, and existence. If we live in a simulation, what does that mean for our sense of identity and purpose? Are we just pawns in a vast cosmic game controlled by entities beyond our comprehension? Or do we still have autonomy despite the limitations of a simulated reality? One of the most troubling aspects of simulation theory is the idea that everything we experience, our relationships, our struggles, our achievements, could be part of a pre-programmed narrative. This leads to existential questions about the value of life in a simulated universe. If our reality is not real in the traditional sense, does that diminish the significance of our experiences? At the same time, simulation theory offers a glimmer of hope. If we live in a simulation, death may not be the end. It is possible that our consciousness is preserved or transferred to another simulated reality, allowing us to continue to exist even after the physical universe has ceased to function. In this sense, simulation theory presents a vision of reality in which time as we know it is not a fixed or limited resource. Could we ever escape the simulation? If we actually live in a simulation, one of the most intriguing questions is whether we could ever escape. In science fiction, characters often become aware of the simulated nature of their reality and attempt to break out of it. But in the real world, how could we know the limitations of the simulation, and would it even be possible to leave it? A potential approach to detecting simulation could be to find inconsistencies or glitches in the fabric of reality. Just as a computer game has bugs or graphical errors, our universe could show anomalies that indicate its artificial nature. Some physicists have speculated that certain unexplained phenomena, such as the behavior of dark matter or the nature of quantum entanglement, could be signs that we are living in a simulation. However, even if we could confirm that we are in a simulation, escaping it could be a completely different matter. The rules of simulation, the physical laws that govern our universe, would likely prevent us from interacting with or observing the creators. Our own thoughts and perceptions could be limited by the limitations of the simulation, making it impossible for us to understand what lies outside of it. In a simulated universe, time could be a flexible or even illusory concept. The passage of time could be manipulated by the simulation's creators, speeding up or slowing down as needed. This opens up the possibility that the end of time as we experience it is not the end of the simulation itself. Instead, our perception of time may be just one layer of a much larger and more complex system, with no real beginning or end. If simulation theory is correct, the ultimate fate of the universe may lie not in the physical processes we examined in previous chapters, but in the decisions of an unknown intelligence that exists outside the boundaries of our reality. Whether the simulation is shut down, restarted, or updated, the end of time in a simulated universe could be both sudden and incomprehensible to us. In the next and final chapter, We will explore what all of these theories and hypotheses, from the Great Freeze to simulation theory, mean for the human experience. How do we make sense of the end of time? And what role do we play in the grand story of the cosmos? Humanity's role in the cosmic end. Understanding the fate of the universe. As we reach the final chapter of our exploration of the possible end of the universe, it is time to reflect on what all of these possibilities mean for us humans. From the Great Freeze to the Great Rip, from the evaporation of black holes to the idea of the multiverse or even simulation theory, we have examined a range of scenarios for how the universe could end. But in the midst of all this cosmic speculation, we must ask ourselves, what role does humanity play in this grand narrative? And how should we approach the end of time, whether billions of years from now or perhaps closer than we think? For most of human history, we have viewed ourselves as central to the history of the universe. Ancient civilizations placed Earth at the center of the cosmos, with the stars and planets revolving around us. The Copernican revolution in the 16th century refuted this belief and showed that the Earth is just one of many planets orbiting the Sun, which in turn is just one of countless stars in the Milky Way. In the 20th century, astronomers such as Edwin Hubble revealed that the Milky Way is just one of billions of galaxies, each containing billions of stars. As our understanding of the universe grew, we began to see ourselves as smaller and more insignificant in the vast cosmic landscape. Yet despite our apparent insignificance, we have a unique point of view. As far as we know, we are the only species in the universe that can deliberate on its fate. Carl Sagan reminded us in his famous reflection on the pale blue dot that the Earth is but a tiny speck in the immensity of space, but it is the only home we have ever known. From this tiny point, we started our journey to understand the cosmos, and therefore the nature of time and existence. In the grand timeline of the universe, humanity occupies an almost infinitesimal fraction. The universe is about 13.8 billion years old, and modern humans have only existed for about 200,000 years. To put that in perspective, if the history of the universe were compressed into a single year, humanity would not have appeared until the final seconds of December 31st. But in this brief cosmic moment, we have made extraordinary progress in understanding the universe. Through the development of science, we have discovered the age of the universe, the physical laws that govern it, and the possible ways it could end. But we are still at the beginning of our journey. There are long periods of time ahead in which the universe will continue to evolve, long after humanity has faded into history. Can humanity survive the end of the universe? One of the most profound questions we can ask is whether humanity, or any form of intelligent life, can survive the end of the universe. As we explored in previous chapters, the fate of the universe could include scenarios like the Great Freeze, in which all the stars go out, and the universe becomes a cold, dark void. Alternatively, it could face a more dramatic end in the Great Ripping, in which galaxies, stars, planets, and even atoms are torn apart by the accelerated expansion of space. Given these possibilities, the question arises, Is there a way for life to continue to exist in such a future? One possibility is that humanity is developing technologies that allow us to survive in increasingly hostile conditions. In the distant future, as stars begin to die, advanced civilizations may be able to harness the energy of black holes, which could remain active for trillions of years before eventually evaporating. The concept of Dyson spheres, giant structures built around stars to harness their energy, could be extended to black holes and provide long-term energy sources for surviving civilizations. If the multiverse hypothesis is correct, it may be possible for advanced civilizations to find ways to escape our dying universe and migrate to a younger, more life-friendly universe. This would require an extraordinary leap in our understanding of physics, particularly in the areas of quantum mechanics and space-time. Theoretical physicists have proposed ideas like wormholes that could provide shortcuts between distant regions of space-time or even between different universes. Another speculative possibility is the idea of digital immortality. As technological advances increase, it may become possible to upload human consciousness into a digital format, allowing individuals to exist within sophisticated computer simulations. In this scenario, human consciousness could continue to exist even if the physical universe comes to an end, by being preserved in a virtual reality, powered by energy sources that extend far beyond the lifespan of the stars. This ties into simulation theory, according to which our reality may already be a simulation. If we live in a simulated universe, the end of our universe could simply mean the beginning of a new simulation. Some speculative theories suggest that advanced civilizations could develop the technology to restart the universe after its ultimate death. In the cyclic universe model, in which the universe goes through repeated cycles of expansion and contraction, a sufficiently advanced species could potentially trigger the next Big Bang, thereby ensuring the survival of life and consciousness in the next cosmic cycle. While this idea is highly speculative, it shows how far we can stretch our imaginations when thinking about the end of time. Even if we accept that humanity will not survive the end of the universe, we still need to think about our legacy. What impact will we have on the universe, and how will future civilizations, or even other species, remember us? One possibility is that humanity's legacy in space travel is preserved. By sending probes, spacecraft, and even human settlers to distant planets and stars, we extend our influence beyond Earth and create a lasting imprint on the universe. In the distant future, long after Earth has become uninhabitable, our robotic emissaries could continue to explore the galaxy, transmitting data and preserving the memory of human civilization. Another aspect of our legacy lies in the information we produce. As we continue to advance in areas such as artificial intelligence, we may one day create machines capable of preserving human knowledge, culture, and history for eons. These machines could continue to work long after humanity has disappeared, acting as archivists of our civilization. Ultimately, our most lasting legacy may be our contribution to understanding the universe itself. By studying the cosmos, we discover the fundamental laws of nature and gain insights into the nature of time, space, and existence. These discoveries will remain part of the collective knowledge of every future civilization, human or otherwise, that continues the quest to understand the universe. Ultimately, the idea of the end of the universe forces us to confront our deepest existential questions. What is the purpose of life in a universe that will one day cease to exist? How do we find meaning in a reality where everything, including time itself, could one day end? For some, knowing that the universe is finite can lead to a feeling of futility or despair. But for others, it's a reminder of the preciousness of life and the importance of making the most of the time we have. Given cosmic impermanence, we are called to live with greater awareness, to appreciate the beauty and mystery of existence, and to contribute positively to the world around us. In the end, whether the universe fades into darkness, collapses in on itself, or continues indefinitely as part of a larger multiverse, humanity's role is to bear witness to cosmic history. As far as we know, humanity is the universe's way of knowing itself, and in this sense we have a unique and profound responsibility. Our exploration of time, space, and the cosmos is not just a scientific endeavor. It is an expression of our curiosity, creativity, and desire to understand the deeper truths of reality. As we complete our exploration of the ultimate fate of the universe, we are left with more questions than answers. The future of the cosmos is shrouded in mystery, and many of the scenarios we have discussed, from the Great Freeze to simulation theory, remain speculative. But this uncertainty is part of what makes studying the universe so fascinating. The answers may elude us, but the journey of discovery continues. In the grand scheme of time and space, humanity is but a fleeting moment. Yet in this moment we have the ability to explore, learn, and marvel at the wonders of the universe. Whether we survive the end of time or not, our quest to understand the cosmos will remain one of the most remarkable chapters in the history of existence. The role of quantum mechanics in the fate of the universe. In our exploration of the ultimate fate of the universe, a fundamental aspect of the cosmos remains both deeply mysterious and incredibly powerful: quantum mechanics. While the large-scale behavior of the universe is governed by forces such as gravity and dark energy, the microscopic realm of particles and quantum fields plays a crucial role in determining how the universe evolves and might ultimately end. Quantum mechanics, the science of the very smallest, regulates the behavior of particles such as electrons, photons, and even the fundamental building blocks of matter: quarks. In this strange and often counterintuitive realm lie many of the universe's deepest mysteries, including the nature of time and the fate of matter. To understand how quantum mechanics influences the fate of the universe, we need to examine some key principles and thought experiments. One of the fundamental principles of quantum mechanics is Heisenberg's uncertainty principle, which states that certain pairs of properties, such as position and momentum, cannot both be measured at the same time with perfect accuracy. The more precisely we know one property, the less precise the other becomes. This is not just a limitation of our measuring devices, but a fundamental property of the universe itself. The uncertainty principle shows that reality at the quantum level is not as deterministic as it appears in our everyday lives. Instead of being made up of fixed, predictable objects, the universe is an ever-shifting sea of probabilities. Particles do not have fixed positions or velocities until they are measured, and even then the results are determined by probability distributions. This probabilistic nature of quantum mechanics suggests that the fate of individual particles, and therefore the entire universe, may not be predetermined. If quantum uncertainty permeates the cosmos, it could mean that the end of the universe does not follow a single, inevitable path. Instead, there could be multiple possible futures determined by the complex interplay of quantum mechanical processes. One of the most intriguing implications of quantum mechanics is the phenomenon of quantum fluctuations. Even in the vacuum of empty space, quantum mechanics tells us particles and antiparticles constantly appear and disappear due to energy fluctuations. These fluctuations are usually short-lived and occur on incredibly small scales, but they are thought to play a crucial role in shaping the universe. In the early moments of the universe, quantum fluctuations may have been responsible for initiating cosmic inflation, which expanded the universe from a tiny, dense point to its present size. Tiny energy fluctuations may have caused regions of the early universe to expand at different rates, eventually leading to the large-scale structure of the galaxies, clusters, and superclusters we observe today. But quantum fluctuations might not be limited to the early universe. Some cosmologists believe that even in the distant future, when the universe is cold and empty, quantum fluctuations could cause new Big Bangs. In a process known as eternal inflation, quantum fluctuations could cause regions of space to expand rapidly, creating new universes in a potentially infinite multiverse. This idea opens up the possibility that the universe as we know it is just one of many, born out of the quantum chaos of space-time. Black holes, the remnants of massive stars that have collapsed under their own gravity, are among the most extreme objects in the universe. As we've already discussed, black holes play a crucial role in the fate of the universe through the process of Hawking radiation, in which they slowly lose mass and energy over time. This radiation is created by quantum mechanics near the event horizon of a black hole, where virtual particles are created and destroyed due to energy fluctuations. One of the most perplexing questions about black holes concerns the information paradox. According to quantum mechanics, information, the exact state of particles, cannot be destroyed. But when something falls into a black hole, all information about its physical state appears to be lost. Once the black hole evaporates through Hawking radiation, the information it contains appears to be gone forever, contradicting the principles of quantum mechanics. Solving this paradox represents a major challenge for physicists, and several theories have been proposed. One possibility is that the information is not actually lost, but is subtly encoded in the Hawking radiation that leaves the black hole. Another theory, known as the holographic principle, proposes that all information falling into a black hole is stored on its two-dimensional event horizon surface, similar to a hologram. This idea has profound implications not only for black holes, but for the nature of the universe itself. Another key concept in quantum mechanics is quantum entanglement, in which two particles become linked together in such a way that the state of one particle immediately affects the state of the other, no matter how far apart they are. This phenomenon has been confirmed experimentally and remains one of the strangest aspects of quantum mechanics because it appears to violate the principle that nothing can move faster than light. Quantum entanglement could also be the key to understanding the nature of space-time itself. Some physicists believe that the fabric of space-time arises from networks of entangled particles. In this view, space-time is not a fundamental aspect of reality, but a construct arising from deeper quantum relationships. If this is true, it could have profound implications for the fate of the universe. As the universe evolves, the structure of space-time itself could change or even unravel as quantum states become more entangled or disentangled. As we discussed in Chapter 2, the arrow of time is closely related to the concept of entropy. But quantum mechanics raises fascinating questions about the nature of time itself. At the quantum level, many processes are temporally symmetric, meaning they can occur both forwards and backwards in time. So why does time only move in one direction in the macroscopic world? One possibility is that the arrow of time is an emergent property of the universe as a whole, arising from the interaction of quantum mechanics and the second law of thermodynamics. In this view, the one-way flow of time is a consequence of the low entropy state of the universe after the Big Bang. As entropy increases, time appears to move forward, but at the quantum level, time may have no preferred direction at all. If time is an emergent property, this raises profound questions about the future of the universe. Could the arrow of time one day reverse, causing the universe to move backwards toward a state of lower entropy? Some speculative theories suggest that time could oscillate in a cyclic universe, flowing forward during expansion phases and backward during contraction phases. But these ideas remain speculative, and our current understanding of quantum mechanics and thermodynamics suggests that the arrow of time continues to point toward the future. At the smallest scales, the fabric of space-time itself is thought to consist of tiny, fluctuating regions known as quantum foam. This foam-like structure arises from the uncertainty principle, which allows space-time to be constantly in flux at the quantum level. Within this foam, tiny wormholes and fluctuations in space-time could spontaneously appear and disappear. In the distant future, long after the stars have gone out and the black holes have evaporated, the universe could be left as a cold, empty void. But even in this bleak state, the quantum foam could continue to bubble with activity, spawning volatile particles, virtual black holes, and even new universes. The idea that the universe could constantly produce new structures through quantum fluctuations offers a tantalizing possibility that the end of time may never actually come. Even in the most extreme scenarios where the universe reaches maximum entropy, quantum mechanics suggests that randomness and uncertainty will always persist at the smallest scales. In this sense, the universe could be in a perpetual state of transformation, with no definitive end in sight. Quantum mechanics, therefore, offers a radically different perspective on the fate of the universe. While classical cosmology paints a picture of a universe heading toward a state of maximum entropy and thermal death, Quantum mechanics suggests that the evolution of the universe could be far more complex and unpredictable. The interplay of quantum uncertainty, space-time, and entropy leaves open the possibility that there could be new beginnings, even in the face of the apparent end of the universe. The far future, trillions of years and beyond. Although many cosmological models predict that the end of the universe is inevitable, the time frames for these events span unimaginable periods of time. To truly understand the distant future of the universe, we need to think in trillions of years, far beyond the current age of the universe. As we venture into this distant future, we will explore the phases the universe may go through, from the gradual exhaustion of the last stars to the final decay of matter itself. In about 10 trillion years, the universe will enter the so-called degenerate era. By that time, most of the stars currently lighting up the universe will have exhausted their nuclear fuel and will no longer shine. The only remaining objects in this dark universe will be the remnants of stars, white dwarfs, neutron stars, and black holes. White dwarfs are the cores of stars that have exhausted their hydrogen supply and shed their outer layers. They no longer perform nuclear fusion, but remain incredibly dense and cool slowly over time. Neutron stars, on the other hand, are the remnants of massive stars that exploded into supernovae. They consist almost entirely of neutrons and are even more compact and dense than white dwarfs. When the degenerate era begins, most of the universe's remaining energy will be trapped in these stellar remnants. Over trillions of years, white dwarfs and neutron stars will gradually cool and become black dwarfs, cold, dead remnants of stars that emit neither light nor heat. The universe, once lit by countless stars, becomes a dark, desolate place. As the degenerate era unfolds, black holes will play an increasingly important role in shaping the future of the universe. Formed by the collapse of massive stars or the merger of smaller black holes, these cosmic giants will dominate the universe as the last major sources of energy. For trillions of years, black holes will continue to merge and grow, sucking up any remaining matter in their surroundings. However, as we have already discussed, black holes are not eternal. Black holes slowly lose mass and energy over time due to Hawking radiation. For most black holes, this process takes an incredibly long time, but eventually, even the largest supermassive black holes will evaporate completely. The evaporation of black holes marks a crucial moment in the long-term evolution of the universe. Once the last black hole evaporates, the universe will enter its final phase, the dark era. In the dark era, the universe will be a cold, empty nothingness. At that point, all stars will have gone out, all black holes will have evaporated, and there will be no new sources of energy left. The only objects remaining in the universe will be subatomic particles like electrons and protons drifting through an ever-expanding, ever-cooling void. But even these particles are not eternal. According to some theories, protons, the building blocks of atoms, could eventually decay. Proton decay is a hypothetical process in which protons decay into lighter particles such as positrons and neutrinos. Although proton decay has never been observed, certain unified theories predict that protons have a limited lifespan. If that is true, then after 10 to the 35 years, the protons will also decay, creating a universe consisting only of radiation and neutrinos. Without matter, the universe will have reached a state of maximum entropy. This is the heat death scenario we discussed earlier, where there is no longer any usable energy to power any process or create new structures. Time, as we understand it, may still exist, but there will be nothing left to experience its passing. Could life survive beyond the dark era? In such a bleak future, it is hard to imagine that life could continue. Without energy, without stars, and without planets, the conditions that made life possible in the early universe will no longer exist. Still, some speculative theories suggest that even under the most extreme conditions, life could find a way to survive. One possibility is that advanced civilizations could learn to harness the energy of black holes or other exotic processes to sustain themselves long into the future. If protons do not decay, it is conceivable that life forms could exist on black dwarfs that use the weak heat given off by these objects to maintain minimal biological activities. Another, more speculative idea is that life could migrate to other universes, either through wormholes or by using quantum mechanical processes. In this scenario, life could escape the heat death of the universe by escaping to a new universe with more favorable conditions for survival. Is the rebirth of the universe imminent? Although the Dark Era may seem like the end of the road for the universe, some cosmologists suggest that the universe may be able to restart itself. As we have discussed in previous chapters, certain theories, such as the cyclic universe model, suggest that the universe goes through endless cycles of expansion and collapse. If this is the case, the universe could one day collapse into a great collapse, followed by a new Big Bang. Alternatively, quantum fluctuations in the empty space of the Dark Era could trigger a new Big Bang, giving rise to a new universe from the ashes of the old one. This process, known as vacuum decay, could trigger the birth of a new universe, with new physical laws, constants, and dimensions. In this view, the death of a universe is not the end of time, but the beginning of a new cosmic cycle. When we think about the distant future of the universe, we are reminded of the incredible vastness of time and space. From the first moments of the Big Bang to eventual thermal death trillions of years from now, the universe has undergone an extraordinary journey. But despite his apparent fate, the story of the universe is far from over. Whether through the creation of new universes or the persistence of quantum mechanical processes, the universe could evolve in ways we cannot yet imagine. Ultimately, the fate of the universe remains a mystery that fascinates the minds of scientists and philosophers alike. As we look to the future, we are left with profound questions about the nature of time, space, and existence itself. Perhaps in examining the fate of the universe, we are also exploring our own place in the grand cosmic story, a story that extends far beyond the limits of human experience and extends into infinity.